This is Physics 2211 Lab 2 going over the motion of a falling object. Now in this lab we will be observing a foam ball that is dropped from rest and moves somewhat slowly, which is essentially just moving slower than a rock dropped from the same height at rest. Now, we'll be taking experimental data from this and placing it into tracker software to extract the actual position over time, and then comparing this to two computational models that predict position over time for scenarios with just gravity acting as a force, as well as gravity and drag acting as forces. Now, this whole lab is based off of something called the velocity update formula, which is derived from the momentum principle, which is also known as Newton's second law. Now, the velocity update formula finds the final velocity when you take the initial velocity, add the net force divided by mass, and multiply that by the change in time. Now, in this scenario, the net force without drag is going to be negative 9.8 times the mass of the ball. We also need the position update formula for this whole lab, which gives you your final position when you take the initial position and add the average velocity times the change in time. This is the tracker video that actually analyzes and extracts the ball's position over time. And as you can see by this chart on the right, it actually starts with an initial velocity of 0 as it gradually speeds up as time goes on. And then the data from this bottom right chart is then extracted to be placed in Excel to compare to the computational models. These are the initial conditions of both calculation loops that predict position over time. And essentially what we do here is we just set the ball's mass, the initial position, the initial velocity, which is 0, as well as the gravitational constant and the drag coefficient, which is 0.0055. This is the calculation loop for the gravity-only scenario, which essentially initially calculates the net force, which is negative the ball's mass times the gravitational constant, and then applies that to the ball's velocity and applies that to the ball's position to continuously update it for multiple timestamps. This is the gravity and drag calculation loop, which essentially does the same thing as the last loop, except this time we take into consideration the force of drag, which is negative the drag coefficient times the ball's velocity squared. And then this is just added to the same net force we had before, and then updates the ball's velocity and then position accordingly. These are the three different data sets and the comparison of them on a graph. Blue is experimental, red is gravity only, and yellow is gravity and drag. And as you can see, the gravity and drag scenario very closely resembles the actual experimental data because that actually happens in real life. And meanwhile, the gravity scenario, only scenario, differs very slightly, with it actually showing that the ball would hit the ground before the gravity and drag scenario, and that's just because there's no air resistance acting on the ball in this hypothetical scenario. Now, which of the two models actually predicts the terminal velocity? So the model with gravity and drag was actually found to predict terminal velocity because terminal velocity is when the force of drag up balances with the force of gravity down, and when these two cancel out, you end up with a net force of 0, and then constant velocity is then achieved, which is visualized on velocity over time graphs as a horizontal line, which while isn't shown on this graph, the gravity and drag scenario alludes to that happening somewhere off the graph. Additionally, because terminal velocity is the balancing of two forces, you actually can't have two forces balance out when you only have one force, so having gravity only could not balance out with anything. Now, what if the ball were thrown instead of dropped from rest? Would the terminal velocity be the same or different? Now, mathematically, what you can do is take the gravitational force and set equal to the force of drag and then solve for velocity. So you end up getting the square root of negative mg over d, and none of these variables are actually influenced by an initial velocity, so we can tell there that it should be the same. And then additionally, graphically, we can see that all three of these different scenarios allude to it having a similar terminal velocity somewhere off the chart. And then additionally, one cool thing, when you actually throw the ball faster than terminal velocity, as seen by the yellow line here, with a negative 7.5 meters per second throw down, it actually slows itself up to meet the terminal velocity because air resistance here actually outmatches the force of gravity downwards. Thank you.